Today we delve into an emerging threat in the autonomous vehicle industry, physical removal attacks on LiDAR systems. This work by a team of researchers at the University of Michigan and the University of Florida uncovers how these attacks can invisibly alter the perception of autonomous vehicles, potentially leading to hazardous outcomes. This study centers on the perception systems that serve as the eyes of autonomous vehicles, or AVs, enabling them to navigate our roads safely. These systems rely heavily on a trio of sensors: cameras, radar, and LiDAR, short for light detection and ranging. LiDAR plays a starring role due to its precision in capturing the depth and detail of the environment in 3D point clouds. However, this reliance on LiDAR also unveils a vulnerability, one that poses significant safety risks not just to the vehicle itself, but to all road users. This research has identified a novel form of attack, which the researchers have termed physical removal attacks, or PRAs. These attacks exploit the very mechanisms AVs use to process and interpret LiDAR data, allowing an attacker to remotely and stealthily remove genuine obstacles from the vehicle's perception. This particular paper covers a laser injection-based PRA. By injecting invisible laser pulses in close proximity to the LiDAR sensor, it is possible to force the sensor to discard legitimate cloud points from genuine obstacles. The implications of such an attack could be extremely dangerous. An AV could be deceived into making hazardous decisions, such as failing to stop for a pedestrian at a crosswalk or not detecting a stopped vehicle ahead. In the face of these vulnerabilities, this work does not merely highlight the problem, but actively seeks solutions, testing the limits of current defense mechanisms and proposing new strategies to protect against these sophisticated attacks. By the end of this presentation, you'll gain insight into the challenges and opportunities in securing AV perception systems against physical removal attacks, ensuring the road ahead is safer for everyone. And now we will dig into the background on LiDAR sensors and examine some of the existing work related to the attacks on them. LiDAR sensors are especially considered more important for AV driving safety decisions over cameras and radars because of LiDAR's higher reliability and accuracy for object detection. Popular AD companies such as Google, Uber, Lyft, Baidu, GM Cruise, and Ford have developed AD frameworks that integrate with the vehicle. These camera and LiDAR-based AD frameworks usually include 5 main modules: perception, localization, prediction, planning, and control. This paper focuses on a vulnerability to perception. This paper also chooses to focus on spinning LiDAR rather than emerging solid-state LiDAR technologies. Typically, 3D spinning LiDARs are composed of a vertical stack of infrared laser diodes with a corresponding stack of photodiodes. Both stacks rotate, and each photodiode laser pair covers a particular vertical angle, forming lines in the resulting 3D map. If a laser beam is partially or totally intercepted by obstacles in its trajectory, the results of the reflection on the obstacle surface, called echoes or returns, are backscattered towards the sensor. The internal timing circuit measures the time between the laser pulse emission and the return at the photodiodes, which is then translated into the distance between the obstacles and the LiDAR. The resulting collection of these raw signals is called a point cloud. Previous work on LiDAR sensors has demonstrated that an attacker can inject fake point clouds at various distances by shining a single laser beam composed of fake pulses precisely synchronized to a spinning LiDAR sensor. These previous works show that objects can be hidden by being built to certain physical specifications, or by injecting new cloud points to add noise to the AV's model. Both of these spoofing attacks work to lower the confidence score of the victim AV's model. In contrast to these previous works that focus on lowering the AV detection model confidence score, the PRAs discussed in this paper directly remove selected cloud points at a lower sensor level before being used as input by the perception module. And now we'll move on to a discussion of how the attack works and the expected threat model one might encounter. The physical removal attack technique cleverly injects invisible laser pulses near the LiDAR sensor, tricking it into ignoring real obstacles like pedestrians or other vehicles. Essentially, a blind spot is created within a specific range from the sensor, an area referred to as the spoofing region. The boundaries of this region are determined by the LiDAR's design and processing system. The upper limit of this spoofing region is called the minimum operational threshold, or MOT. The attack synchronizes these invisible pulses with the sensor's firing sequence, allowing researchers to precisely eliminate crucial data points that represent obstacles from the LiDAR's view. The success of the attack depends on manipulating the attack angle, which is the portion of the LiDAR's field of view which can be affected by spoofed signals. By adjusting this angle, obstacles can be hidden from the autonomous driving system's perception, raising significant safety concerns. This attack assumes the goal of the attacker is to compromise the safety of an AV. The attacker is expected to have prior knowledge. They could learn the behavior of specific LiDAR models from publicly available documents like manuals, datasheets, and open source code. They can also be expected to test their spoofing technique on personally acquired LiDARs of the same model as the victims. This spoofing attack requires less fine-tuning from previous versions, as points only need to be spoofed within the MOT. Aiming and tracking can be done through well-known machine learning techniques by collecting LiDAR sensor images from publicly available sources or pre-trained models. Attackers could impact the safety of vehicles in multiple ways. The spoofing device could be placed on the roadside, perhaps near a crosswalk, to shoot malicious lasers at passing AVs. The device could also be placed on a following vehicle to impact the navigation of the vehicle in front of it. This attack mainly works for two reasons. First, LiDAR sensors intrinsically prioritize particular echoes, i.e. the strongest. And two, LiDAR sensors automatically filter cloud points close to the LiDAR sensor enclosure. This attack exploits the first weakness by injecting strong laser pulses. The strong pulses are prioritized over the weaker pulses generated from genuine objects in the distance. Additionally, if you can make the LiDAR unit think that its beams are originating below the firmware-based threshold, you can ensure that those points get ignored. In this image, you can see a PRA performed on a traffic cone. In image A, there is no attack, and in image B, you can see the spoofed points in red, and now the cone is no longer being detected. And now we'll look at some of the preliminary analysis on PRAs, including the design of the attack, the capabilities of the attacker, removing obstacles, the effect on AV's perception models, and the impact of fusion. The basic design of the system is as follows. Pulses from the LiDAR unit are captured via a photodiode, PD here in this graphic. The pulse info gets fed into an oscilloscope through a trans-impedance amplifier, TIA here. The oscilloscope generates a trigger output synchronized to the LiDAR scan interval. This output gets fed into a function generator, FG, which generates a sequence of voltage pulses. The voltage pulses drive the laser diode through a gate driver. The returning pulses can be used in a physical removal attack. To test this setup, researchers used a Velodyne VLP-16 LiDAR sensor. They ran tests in an indoor setting to determine the maximum attack angle that produced consistent results. The LiDAR sensor was placed 2.5 meters from the spoofer, and the attack angle was gradually increased from 0 degrees. For attack angles less than 45 degrees, the number of removed points increases linearly. 45 degrees was determined as the maximum attack angle to produce stable results. PRAs are limited by two factors: the limited receptive field of the photodiodes on the LiDAR system and the limited output power of the laser diodes in the spoofer setup. When the spoofer is out of the receptive range, the spoofed signals are not received by the LiDAR system, so the removal attack fails. And when the signal is too weak to spoof the points, the removal attack also fails. The goal of this attack is to remove an obstacle from view of the LiDAR sensor, so the researchers tested this on a standard traffic cone. The cone was placed at 2, 3, and 4 meters from the LiDAR sensor, and the attack angle was gradually increased to observe the number of removed cloud points. As expected, the attack angle required to move the traffic cone from LiDAR perception decreases with an increasing distance. The attack was able to completely remove the traffic cone point cloud with an attack angle of 6 degrees, no matter how far the cone was from the LiDAR sensor. The perception module in AVs is the core module that leverages machine learning models for object detection. The output of this module directly influences the AV's safety-critical driving decisions, such as collision avoidance. The researchers devised a simulated on-road scenario to see how PRAs affect the confidence scores of these modules. They used the commercially available Baidu Apollo perception module on both pedestrian and vehicle data. Figure A here represents pedestrians, and Figure B represents vehicles. The red line on both these graphics indicates the required confidence score from Baidu Apollo. For pedestrians, an attack angle of just 3 degrees is needed to reduce the confidence below this threshold. For vehicles, an attack angle of 15 degrees is needed to bring this below the threshold. The results demonstrate that the perception model's confidence drops quickly as the attack angle increases, and the models fail to detect an obstacle even when the obstacle point cloud is not fully removed, especially in the case of pedestrians. Fusion in AV models helps compensate for the accuracy limitations of using individual sensors, and it can provide additional robustness against naive black box attacks on AV perception modules. The same setup described on the previous slide was used on 3 commercially available fusion architectures: Frustum ConfNet, AVOD, and AutoWare Integrated Semantic Level Fusion. These results confirm that PRAs can cause severe performance drops and failures even if fusion is implemented. To conduct a removal attack in the real world, the researchers considered the following scenario where autonomous vehicles is driving forwards, approaching a static obstacle in the center of the AV trajectory, and the attacker's spoofer is located on the side of the road. The goal of the attacker is to remove the obstacle from the 3D map of the LiDAR sensor. The researchers considered 2 sets of evaluation: 1, the attacker capability in outdoor scenarios, and 2, the impact of the attack on the driving decisions by evaluating end-to-end scenarios on prediction, control, and planning using industrial-grade simulator LGSVL. First, attacker capability was tested in different outdoor scenarios. First, the distance between the LiDAR sensor and the spoofer was gradually increased to evaluate the number of removed cloud points. As distance increases, the number of points removed decreases. This is mainly due to the limitations of the spoofer setup. For instance, the intensity of the spoof signals decreases as the distance increases, weakening the overall attacker capability. This setup was also tested in different light conditions. It turns out that attacker capability is reduced in daylight. This is suspected to be due to the hour found in natural light interfering with the sensors on the LiDAR unit. To further analyze the impact of PRAs, the researchers used the LGSVL simulator, LVSGL is an open-source, production-grade simulator designed for testing and developing AD frameworks. To simulate PRAs, the researchers synthesized the sensor input changes corresponding to attacks found in real-world tests. Results of the simulation show that PRAs can cause AVs to fail to brake and stop before colliding with an obstacle, even if the obstacle is inside the attack region for only 40% of the entire AV's route time. Results show that starting the attack from further away leads to higher chances of collisions. Even with limited capabilities of attack angles, the removal attack can lead to severe consequences for AVs, like collisions. And now looking at PRAs on moving vehicles. There are two main challenges for attacking a moving vehicle. The first is synchronizing with the LiDAR sensor, and the second is aiming the spoofer at the LiDAR unit. Synchronizing with the LiDAR using a single photodiode at a fixed location is difficult since the LiDAR scan is sparse at a distance. This limitation is further aggravated when the AV is moving. To overcome this challenge, the researchers used a larger optical setup to increase the receptive field so that the LiDAR signals can be captured by the photodiode. However, the effect of this is limited and dramatically increases weight of the spoofer unit. Also, aiming at the LiDAR unit presents another challenge, as real-time tracking of a small moving target is difficult. To overcome this challenge, researchers used a 3D printed laser holder on top of a robotic turret. This turret was then controlled with advanced tracking algorithms to keep the beam pointed at the LiDAR sensor. The researchers conducted two experiments with this setup. One case where the LiDAR unit was placed on top of a robot, and another case where the unit was placed on top of a car. In the robot case, researchers aimed to analyze the performance of the tracking system with a controlled environment. For the car case, researchers aimed to demonstrate the feasibility of attacking the AV in the real world with the proposed tracking system. This figure shows the percentage of points removed from the target pedestrian using the robot. Note that the obstacle is not fully removed in several frames in both of the scenarios, due to imprecise aiming. This table shows the success rate of the attacks given different removal percentage thresholds. And now we'll look at some of the existing defenses for such an attack, and also some of the proposed defenses by the researchers to mitigate these attacks. Prior research has provided defenses against spoofing attacks. These previous defenses are meant to catch the injection of new cloud points to create objects that aren't really there. They're not necessarily meant to catch the removal of existing objects. This defense can introduce false negatives. It may mistake genuine detection of partially removed obstacles as spoofing and discard them. Another defense uses 3D shadows to detect the existence of hidden objects. This method has a 100% true negative rate, but a 0% true positive rate. A 100% true negative rate means that every time there was no attack, the defense correctly identified that there was no attack. A 0% true positive rate means that the defense failed to detect any instances of the attack when the cloud point of obstacles was removed. The researchers proposed two defense methods against PRAs. The first of these is fake shadow detection, or FSD. This is an extension of the hiding attack defense discussed on the previous slide. The FSD methodology consists first in identifying the shadow regions of the point cloud. Then, the shadow regions are compared with the expected shadows of the detected objects using Euclidean clustering. This comparison is achieved by projecting the point clouds of a detected object on the ground and filtering out the corresponding shadow region. If the remaining shadow region is above a threshold, it is considered a removal attack. This method alone results in an 82.5% true negative rate and a 91.2% true positive rate. Still, FSD is computationally expensive, and as such, there is still room for improvement. Since PRAs remove cloud points along a specific direction with respect to the LiDAR, a simpler and more practical solution to detect the removal attack is to look for disparities in the raw point cloud data. This can be accomplished by inspecting the horizontal angular view of the LiDAR, or azimuth, as the removal attack would create a cloud point gap along the entirety of the attack angle. Thus, the approach consists of calculating the azimuth values of all the cloud points in the scene and sorting them in increasing order based on the calculated values. Missing cloud points will correspond to missing azimuth regions that in turn can reveal the attack. A combination of FSD and azimuth-based detection leads to 99.98% true negative rate and a 100% true positive rate in the simulation, and a 100% true negative rate and 100% true positive rate on the physical VLP-16 LiDAR unit. In this paper, researchers have discovered a new physical removal attack which removes LiDAR point cloud from genuine obstacles. This study explores the attacker capability to use the point cloud ablation at the sensor level to cause the perception module to fail to recognize obstacles and their locations, researching an attacker capability of 45 degrees. The researchers then evaluate the effect of PRAs on 3 AV perception and fusion models. They also achieve a 92.7% success rate at removing 90% of target obstacle cloud points on a moving vehicle. Finally, they propose 2 effective defense strategies to help mitigating the threat. Please let me know if you have any further questions.